Hello everyone, my name is Charlie Keaney and I'm software toolchain engineer at MCOSM, and in the audience is my collaborator Chunyu Liao, who is a staff member at PLCT. The Open Hardware Group is a consortium of organizations across industry and academia with the mission to produce high quality, free and open source hardware and software IP. For our talk today, we are going to focus on the Core 5 family of processors, which are based on the RISC-V ISA. Specifically, we are going to focus on the CV32E40P processor, which is a microcontroller in the Core 5 family. This project was carried out as a team effort across various organizations. The original work was carried out by the University of Tübingen. The ongoing work is now carried out by MCOSM and PLCT. MCOSM is a software consultancy company specializing in software toolchain technologies. The Programming Languages and Compiler Technologies Lab, PLCT, is a part of the Institute of Software at the Chinese Academy of Sciences. The CV32E40P is based on RISC-V, specifically on the RISC-V machine architecture or v32 iMac. It adds the ZFNX standard extension and 8 custom extensions shown on the slide. These include extensions adding hardware loops and immediate branching, memory access with post-increment, extensions to the ALU operations, and an operation to synchronize multi-core processors. Most significantly, it adds non-standard bit manipulation and SIMD extensions from the PULP project at ETH Zurich and the University of Bologna. In total, 323 new 32-bit instructions, with the majority for SIMD support, all using the custom free encoding spaces. So what is our goal? Our goal is to develop a commercial-grade LLVM toolchain for the CV32E40P. This is a toolchain that is of a high quality, is robust, conforms to standards, and is maintainable. Now I'm going to talk about our approach. Our overall aim is to work from the bottom up, incrementally adding as necessary. Firstly, we decided that we are using the LLVM MC layer assembler, as we could reuse and extend the standard RISC-V implementation for this. For the linker, we decided to reuse the existing implementation of the RISC-V GNU linker LD, as it already has the custom relocations we need. Since our target is a microcontroller, we chose GNUlib for our C library. This library is suitable for embedded bare metal use. Next, we decided how code generation would be implemented and to what extent built-ins would be used as a supplement to automatic code generation. The final stage of our approach is to work on adding optimizations as we find them to improve the code produced. While we were trying to develop Core 5 LLVM, we encountered various challenges and opportunities. In the following slides, I will discuss each of these in turn. Because there was no built-in spec, we had to think carefully about what built-ins to include. We came to the conclusion that there are many instructions for which it does not make sense to add built-ins. For example, adding built-ins for individual loads and stores to registers is not terribly useful. Similarly, built-ins are just not appropriate for changing flow of control. We created names for our built-ins conforming to the RISC-V standard. We also included standard built-ins such as built-in ABS where appropriate. The specification that we created was then taken through the official Open Hardware Group process for ratification. Users assume that their compilers are interchangeable, so compatibility between Core 5 LLVM and GCC is important. This is not just a challenge, but an opportunity. When the compilers are compatible, they can use each other's test suites. This means GCC regression testing can find issues with LLVM, and LLVM testing can find issues with GCC. This builds on the strength of both compilers, improving both LLVM and GCC as a result. As an example, for our project, we compared the output of the Core 5 LLVM assembler against the Core 5 GCC assembler, and identified problems not just in LLVM, but also in the GCC implementation. The main way in which we assured compatibility of GCC was by making sure to maintain close and regular contact between the Core 5 GCC and Core 5 LLVM teams. We were faced with the challenge of how to sufficiently test our project. One obvious choice is lit testing, given that we are working on the LLVM project, but we supplemented this with GNU regression testing. Our GitHub repository also includes continuous integration, which runs LLVM lit and all patches submitted. We also compare the LLVM integrated assembler directly against the GNU assembler test suite, thanks to work by Funan Zhang. This identifies inconsistencies between Core 5 GCC and the Core 5 LLVM assemblers. Once we find these inconsistencies, we manually investigate to verify which assembler is producing correct behavior, responding appropriately by coordinating with the Core 5 GCC team. It is easy to program an Nexus A7 to run a CV32E40p core. The problem is we only have a small number of FPGA boards. As an alternative, we can use simulation. One of the benefits of using a simulator is you can simulate many processors in parallel as you're not constrained by the availability of hardware. There are presently 2 simulator options. You can either use the Core 5 Verilator model or you can use the Core 5 QEMU target. However, the QEMU target is still under development. For this reason, we focus our pre-silicon testing on using the Verilator model simulator. This project has proved a great opportunity to train new LLVM developers, of which I am one. We meet weekly over Zoom with both new and experienced developers joining the call. These calls take the form of an in-depth technical review process and usually involve things like screen sharing code and demos. These calls are then supplemented by a variety of synchronous and asynchronous communication methods, including public Mattermost and email. If you would like to get involved, then please speak to Chunyu, Lewis, or me. Here are some details on the slide that I think you may find useful if you are interested in Core 5. Thank you for listening.